Hello and welcome to this module, module 10. In this module, we are going to see about register transfer level. And again, we have two modules based on register transfer level components. In the first module, that is module 10, we will see about the combinational components. And then in module 11, we will see about the sequential components. So first we will, in this particular module, we will first see about what is register transfer level and what is register transfer level design. And then we will see about the components of register transfer level. So what is register transfer level? It's a kind of a design abstraction which models a synchronous digital circuit, that is the complete circuit, which is synchronous. That means it is synchronized by using a clock, and it also depicts the flow of digital signals, that is data, between hardware registers and the logic operations or arithmetic operations. So here is our level of abstraction. So whenever we try to design digital circuits, we can actually go from, let's say, designing circuits at a transistor level and then make gates out of transistors, and then we can actually do RTL or register transfer level, and then go up into transaction level. So this process, as you design circuits from transistors to gates to RTL, this is actually called as a bottom-up approach. And in some cases, you can also go designing at a register transfer level and then go to gate level design and then the transistor level design. So this is actually usually called as a top-down level. So as a computer engineering professional, we usually adopt the top-down approach. And for example, an electrical engineer working in VLSI design would go for a bottom-up approach where they design transistors and using some VLSI CAD tools, and then they create bigger gates, and then they create registers and ALUs and everything from bottom up. Okay, so the transaction level is again a higher level of abstraction where the details below are just simply hidden, and so you more focus on the communication aspects between the modules, and the underlying functionality of the different hardware components is totally hidden. So another definition of what really register transfer level is let's say if you want to perform an addition of two 4-bit numbers. So let's say you have A, which is a 4-bit number, and then let's say you have B, again is a 4-bit number, and now we want to perform these two numbers. You want to add them, and then you want to store them in another, say C, let's say a 5-bit number, because you want to also take care of the carry. So when I want to do this, so therefore typically if I want to design a circuit for this, so let's say I need to have a register which can store 4 bits. So this one I need to actually create a register, and we know that we can create a register either using a latch or we can actually use even a flip-flop and make a register. So then we also need to create another register which is for B, and we need to somehow figure out a way in which we have let's say a 4-bit full adder over here, and you have inputs that are coming which are A and B, and then this, obviously the full adder is going to have a C in and a C out, and then we have to figure out a way to then define a 5-bit C register, and C in C out is stored in here. The 4 bits here are stored in. So somehow we need to actually create such a design. So this is basically what is called as a register transfer level. So we are talking about how information from registers flow into the logic operation or arithmetic operations or any data operations are performed, and then again how it flows back to another register storage. So that's basically defined as RTL level of abstraction. So whenever we want to actually do more complex operations, say for example you're just not interested in just performing addition, but you want to perform subtraction, you want to perform increment, decrement, you also want to perform all type of logic operations like AND or XOR, whatever it is. And then let's say even if you want to say you want to have a multiply operation or a division operation, so all these complicated things. So we need to actually now come up with the circuit that performs all this, and on top of it also you need to make sure that you are able to take it from an array of memory, 2 values, and then perform the operation and then store it back into that memory. So it becomes a little bit more comprehensive, and therefore what we do is we go for something which is called as a standard processor architecture. So the standard processor architecture is an RTL based circuit for developing standard processors, and we divide this standard processor architecture into 2 components. So one is your control unit and the other one is your data path. So this together we also refer it as the CPU, so which is also referred to as the central processing unit. So the data path itself, as you can see, is simply a collection of functional units such as arithmetic and logic units or multipliers, which is this, or the ALU, generally referred to as the ALU. And then in order to perform the operations, it needs registers either below or above. So it might also require an array of registers. We call that as a register file, and on top of it also needs some kind of a support circuitry to actually interconnect the buses. So that's the bus. Bus is nothing but a collection of wires or signals, and then it also needs some selection logic or enable logic. So in this case it's a mux or in a tri-state buffer. So all these components go into the data path, and usually these components are referred to as the combinational components of it. So the data path itself is only able to perform a certain operation and it's able to store somewhere. But if I want to perform different operations and I want to read from different memory locations and I want to write it to different memory locations and I want to do these in a sequence, then that is performed using the control unit. And as you can see, the control unit is nothing but your FSM. So therefore, as you can see, the standard processor architecture consists of your data path, which is the combinational logic, and then your control unit, which is nothing but your sequential logic. So you put these two together and make your standard processor architecture. Later on we will see that this process is very cumbersome, and then this entire thing is actually replaced by a code, and we specifically say that code as a microcode, and thereby you get something which is called as a microprocessor. So the combinational components in the data path, that's what we're first going to see, includes device or components that can perform arithmetic operations such as addition, subtraction, and if you want multiplication, division, etc. Logic operations such as AND, OR, XOR, NOT, XNOR, and so on and so forth. Comparison operations like greater than, equal to, less than. Bit manipulations such as shifters, shift registers that can perform left shift, right shift, left rotate, right rotate, extraction and insertion. It also requires interconnection components such as selectors, which are nothing but multiplexers, and interconnect components for buses is nothing but your tri-state gates. And then you have conversion components like decoders, encoders. So these are all used to address your memories and so on. And then you also have some other universal components, memories like ROM, programmable arrays, and so on and so forth. So remember that these ROMs are made up of latches and so on and so forth. So here is some of the basic components which we already seen in CpE200. So we have our multiplexers, we have our tri-state gates, encoders. Here is a simple example how we can actually use a tri-state gate to select different buses, individual buses, to a single bus. So based on these encoding signals, so we can either push A into this bus or push B into this bus or C into this bus and so on. So the tri-state gates are used as components for bus interconnections. And then we have your ROMs. So here you can see internally ROMs are made up of decoders, and we have a memory array which is nothing but latches arranged in a two-dimensional form. Some of the advanced components that we're going to see, because we're going to go towards our main component. As you can see, the data path itself is dependent on the ALU, which is the arithmetic and logic unit. So we are going to go towards it. So we will first see about the arithmetic part of it, and how we can then incorporate the logic part of it, and then how you can create an ALU. So here is a simple full adder. So the full adder consists of, as you can see, has two inputs, X and Y. It has a carry in and a sum out and a carry out. So these two are your outputs, and these three are your inputs. So that forms a full adder. And as you can see, we can also cascade full adders and make it as an n-bit n-bit adder. So in this case, we have a 4-bit adder because you have 4 full adders. And this particular configuration is actually called as a ripple carry adder, because what happens is, in order for this sum S1 to be created, it actually needs the carry out from the previous stage, and similarly for S3 to be calculated, it actually needs this carry, which is dependent on this carry, which is dependent on this carry, and so on. So therefore you can see that the carry has to ripple through the adder circuit in order for you to actually compute the entire sum and the final carry out. So this is a form of a serial operation, and so we need to actually have 4 cycles before you get to a stable result. So the next logic that or the arithmetic logic that we're going to see is the subtractor. So this is actually the truth table, the circuit diagram, and the Boolean logic for the subtractor. So here you can see we have a full subtractor, which is basically has a borrow and has two inputs, 1 bit each, and then you can see that we have an output, which is the difference, and the borrow to the next stage. So this becomes a full adder, and then you can also cascade these and make it as an n-bit subtractor, or let's say, for example, a 4-bit subtractor. Next, we see an adder-subtractor combination. So it is actually possible to do an adder-subtractor combination by actually modifying our ripple carry adder, as you can see here. And over here, we are basically using some XOR gates. So by using these XOR gates, what actually happens is that we can pretty much convert our second value or variable into the 2's complement. So therefore, by XORing, so we can see that we are actually creating a complement, and then by making sure that the carry in is equal to 1, so we can, so this will complement, will do a 1's complement, and then you add plus 1 will make it as a 2's complement. And then we know that whenever we do subtraction, we can also add the 2's complement value to the previous variable, and that would actually be a subtraction. So as you can see, so we can actually simply, instead of actually having a separate subtractor, we can also have a adder-subtractor module. So next we move on to our ALU. So here again you can see that we are having a full adder, which is in the ripple carry adder, and now we introduce 3 elements. One is called your logic extender, the second one is your arithmetic extender, and then you have your carry extender. So whenever we want to perform our logic operations, that is, logic operations includes AND, or NOT. So here you can see that this logic extender is the one that actually performs for every bit, it performs it, and then the full adder basically does nothing. So you get a result which is here, which is basically only based on your logic extender. So whenever we have an arithmetic operation, which is all these, which are addition, subtraction, increment, and decrement, so then the arithmetic extender and the full adder are in play, and they would actually perform these operations. So that's how this is set up. And then again, based on the subtraction or a decrement, so here you can see the control or the carry extender also. So if I'm actually doing a subtraction, then this would actually, you can see there is some XOR functions that are there, and then you have a carry which is also has to be 1. So as we saw on the previous slide, the carry extender plays a role in the subtraction and the decrement. But as far as our register transfer level, so we are not really interested in this type of implementation. We are not going into the detail, so we basically will be identifying that as a block, because this is our ALU. Just consider this as an ALU. So we are now going to have like 2 registers, whatever it is, which are going to be 4 bits, are going to be supplying those values for A and B, and then we get a result which is F. And then you can see that we can use these S signals, which are these select signals, and then we can perform these operations. So in our RTL level implementation, we are only interested in what these signals are and what operations are actually performed. So this 2 table, which is the ALU function table, is what is important to us. So the other components include comparators, so where we can take 2 2 bits, or 4-bit values, 4-bit values, and either compare whether they are greater to 1, x is greater than y, or x is equal to y, or x is less than y, or in some instances if they are equal or not equal to, or in some instances if they are just simply equal to a particular greater than or less than a particular value, or in some instances if they are just simply x is greater than equal to y and x is less than y. So you have different possibilities in which you can design a comparator. So in the case if you want to also have an ALU that does a multiplier, so here you can see that we have a multiplicand and a multiplier, and we can actually perform this multiplication by either using a serial method or a parallel method as shown here. So this is basically a parallel multiplier, and then this is a serial multiplier. The serial multiplier works on the principle that if your multiplier has a 1, then you add the multiplicand to the sum, and then you do a shift operation, and then again you can see that if you have a 1 again, you take the multiplier, add it to the sum. If you simply have a 0, you simply shift it, and so on. So then you get the result. So this particular entire thing is basically mimicking that based on the value of the multiplier, whether you want to add to the sum and shift it, or if you want to simply shift it. So in this module we saw what is RTL design, and then we also saw about different RTL components, specifically combinational RTL components that are used in the RTL design.